Okay, so let's get started again. So we're talking about error models, and if you remember, we started by talking about a model that says we have errors that occur, bit errors that occur independently in the code word. So the probability that E takes on a certain pattern is the product of the probabilities that E0 is equal to U0, etc. And then we ended up at the following equation says something that the probability that the error is such that we have exactly L bits in it, L errors in it, and it's then this expression. So that's one model, and that model is good where we transmit, that we transmit bits bit by bit, and they go over the channel, and then they are in error or not. And whether they are in error or not does not depend on the previous bit errors or the past bit errors, right? So we transmit bits individually, they're treated individually and independently by the channel. Okay, so that's one model. The second model that we are that we talked about is, let's see, another extreme case where the errors occur, the error patterns, all error patterns are equally likely. So we can think of that as an extremely noisy channel, or when basically we have some type of catastrophic error on the way, you know, hardware failure or something like that. So what the receiver gets is a random bits. It's a sequence of random bits, which has nothing to do with what's actually transmitted. But still we would like to be able to detect that event, right? Because hardware failures happens. For this particular model, due to its simplicity that each error pattern, all error patterns are equally likely, 1 over 2 to the power of 1 over 2 to the power of n, then we can actually compute the probability of undetected errors, and it turns out to be 1 over 2 to the power of n minus k, where n is the number of bits in the code word and k is the number of information bits. So n minus k is the number of check bits or parity bits. So here we see the code here is really irrelevant, how the code words are placed, the minimum distance and so forth. The only thing that matters here is the ratio between the number of code words and the number of possible n-bit patterns. Okay? Or stated in another way, the only thing that matters is the number of check bits in the code. Nothing else in the code is important. Okay? While for the case where we have independent bit errors, oops, I don't want to do that. In the case where we have independent bit errors, then the minimum distance is important, because then few bit errors are more likely to happen than many bit errors. Okay, then the minimum distance is important. Okay, so now we have one more error model to talk about, and let's see what is important in that case. And this is something called burst errors. And a burst error is perhaps most easily explained with an example. So again, what is an error pattern in this case? The error pattern is zeros and ones in the error positions. So suppose we have no error until we get our first bit error here. And then there is a correct one, etc. 1, 0, 1, maybe like this. Sorry, let me do this more explicit than that. Suppose we have here 0, 1, 1. Okay, so we had an error, no error, 2 errors in succession, and then we have no error, and we keep on having no errors for a while, and then we have maybe an error event again, 1 here. And then there are 3 consecutive errors, 1 with no error, and then 2 consecutive errors, and then 0 again, and keep on being 0 for the rest of the error pattern here. Okay. So what we have here is we have different phases one might say, of the error pattern. First, everything is okay, and then we have a cluster of errors, and then no errors, and then a cluster of errors like this. Another way to say a cluster is a burst of errors. So we have no errors and then a bunch of errors. Actually, sometimes no errors, but there is a bursty nature here, and then we have a burst here. So we call the first error event here, where it starts and ends here. So this is a burst of length 4. Okay. Why is it length 4? Well, length 4 is the, we count the first and the last one, and we count how many bit positions there is between the first and the last error. Okay, so that happens to be 4. Now, there are only 3 errors in this burst of 4. Okay, so a burst is not the same as the number of errors that occur. The burst is the length of the error pattern where we have errors. Okay, so it's the length of the from the difference from the first position to the last position of this error event. Okay, so here we have a length 4 burst error, which actually contains 3-bit errors. Okay, so I hope the distinction is clear. The burst length is the difference between the first and the last position of this error event. Okay, so and the last burst here, what is the length of that? Yeah. So here we have 6 bits involved in this burst. It happens that 5 of them happens to be 0. But it's a burst of length 6 must have at least 2 errors, one here and one here. But then the rest of the bits could be true, right? Could be correct. So at least 2 errors, at most 6 errors. And all of those patterns in between there are possible. So these things happens also in practice, and it happens when sequence of bits are somehow communicated that in a way that depends on each other. For instance, it could be that these 4 bits belongs to a symbol that carries 4 bits, and if that symbol is in error, and we can't do gray coding or anything like this, then all possible bit patterns of length 4 are equally likely. So when we make a symbol error, all of these 4 bits are scrambled somehow. Or it could be other things. For instance, when we read off a compact disk, then bits are encoded as in this CD, and if there is a scratch in that CD, then a bunch of adjacent bits are affected by this. So that also gives you a burst error. Third example is when transmission over a wireless channel, and sometimes the wireless channel, there is a burst of interference that makes all these bits affected. For instance, there might be a lightning strike or something like that, a lot of interference during the lightning strike, and then these bits gets destroyed. Yes?
How do you separate bursts?
Very good questions. So why is this? Why do we have 2 bursts here and not 1? And the answer to this is that there is no clear definition of this. So my next bullet is to say that these bursts, there are no good models for this. Okay. There are no good models for this. Actually, if I should think about, okay. Actually, one can think of this as being, one burst. Okay. The problem is, since we don't have any good models, there is no probability for these events to happen and so forth. But regardless, we would like to say that the code is able to handle burst errors, but we can't really calculate the probability of this happening. But still, so we want to say that a code can handle single bursts of length L, say. Okay, so with single burst, I mean that there is only one burst error in the code word. Okay, so if we make an example here, so length 3 bursts are then 3 bits. And what are the error events here? These bursts could be 0, 0, 1. Okay, sorry. Let me go back. It should be 1 here and 1 here, and then it could be 0 in between, or it could be 1, 1, 1. So these are the possible bursts of length 3. Right? And then the code should handle these at any position in the error vector E. Okay. So we have these two patterns, 101 or 111, and they could happen anywhere in the E vector. So we don't know, we didn't say how long the E vector could be, but you should be able to handle all of these events. Right? So 3 bits was probably a bad one, but say 16 bits, any 16-bit patterns in the code board should be able to handle that. Okay. And unfortunately, one just has to go into the actual, what one do then is to go into the code construction and look at these patterns and see, okay, does these bursts not cause undetected errors? And we will see a few examples, and hopefully this will clarify. Okay. Questions on burst errors? Okay. So let's go and look at particular codes, constructions which are used in practice, and say something about their capabilities. And the first one, and the simplest code that we can think of, is single parity check codes. And these are codes which has a single parity bit or a single check bit. Check bit and parity bits is the same. So we have, they are also systematic codes. So we have here our information bits, B0 up to BK minus 1, our K information bits. And then the parity check bit is just the modulo 2 sum of this. Okay, which is equal to 1 if the Hamming weight of the information word is odd and 0 otherwise. Okay, so for each, if we have an odd number of ones here, then the parity is 1. If we have an even number of ones here, the parity is 0. Okay, so if we then add the parity bit to the information bits, we see that the modulo 2 sum of this is always 0. Okay, so whatever this is equal to the, okay, so the first part here is equal to P0, right, by construction. So we get P0 plus P0, and that's equal to 0. Okay, so this is called even parity sometimes. So code rate of this is we have k bits, information bits. We have k plus 1 code bits, right? So we have k plus 1 bits here. So the code rate is quite high. It's 1 minus 1 minus k, 1 over k. So when k is large, then the code rate is very close to 1, which is the best we can hope for. Minimum distance is 2, which is pretty poor. Okay. But it means that all single bit errors can be detected. Okay, why is this the case? Well, I mean, if we have, say, k is equal to 2. We have 0, 0, 0, 1, 1, 0, 1, 1. These are the possible information bits. And then, so this is D. So D, our bits are 0, 0, 0, 1, 1, 0, 1, 1. And then the parity bit is only 1. So what's the parity when we have 0, 0? 0 plus 0 is 0. 0 plus 1 is the parity when we have 0, 1 is 1. The parity 1, 0 is 1, and this is 0. Okay. So if we look at then the code word, consisting then of 0, 0, 0, 0, we have, even parity because it's an even number of ones here. Here we have 2 1s, 2 1s, and 2 1s. Okay. So when we receive the pattern 0, 1, 0, do we declare an error or not here? Error. And why is that? Yes, we have an odd number of ones in here. So this one will give error. Okay. But suppose we transmitted 0, 0, 0, and then we add on the error 1, 1, 0 to this. Then we get 1, 1, 0. Do we declare an error here? So this is C plus E, and this is equal to Y. So when we see 1, 1, 0, do we declare an error? Or not?
No error.
No error, exactly, because we have 2 1s here. Looks like a valid code word. We have here 1, 1, 0, it's a valid code word. We declare no error, but we saw that an error did occur here. So it cannot handle 2-bit errors in the same code word. All of those will lead to undetected errors. So, but single-bit errors can be detected, but 2-bit errors cannot be detected. 3-bit errors can be detected. 4-bit errors cannot be detected. As a matter of fact, all error patterns with an odd number of errors will be detected. All error patterns with an even number of bit errors will not be detected. So half of them we can handle and half of them we cannot handle. Okay. So the single parity check code is a rather weak code, but it's also heavily used. Why is it used, do you think?
It's not so complex.
Yes, so that's one important thing. It's very simple, extremely simple to do. You can do this with low-cost hardware and so forth. So these are used in memories, for instance, where complexity is very limited. And in the early days where electronics were expensive, this was used heavily. And it's also good enough if we don't have many errors, right? So suppose that single-bit errors occur, but they occur very rarely, which means that 2-bit errors occur almost never, right? Then we can handle single-bit errors in an cost-effective way. Okay, so it's good for good channels, and it's low complex, so it's heavily used for those applications. Now, if that's not good enough, then we need to do something more advanced. So there is a whole slew of codes, but let's talk about something which is of interest here, and that's the internet checksum. So it's used for error detection in TCP and UDP and IPv4, but only for the header information, not for the payload. So it's only to protect the headers here. And the reason for this is that the headers are super important pieces of information for the protocol, because if the headers are wrong, then the addresses could be wrong and so forth, and we just transmit data in the wrong direction and so forth. So anyways, it works on blocks of bits of any length k, so it's not a specific k. We can use k equals 1, 2, 3, 722, whatever, right? It works for an arbitrary length of k bits. And here how it works. It starts by splitting the data into 2-byte or 16-bit blocks. Okay, 2 bytes is 16 bits. And then we pad with 0 bytes if necessary. So whatever data we have, we split that into a number of sub-blocks, all of these being 16 bits long. And then we add them as 16-bit integers using one complement addition, denoted as plus prime here. I'll show an example in the next slide to explain how this is done. So the 16 parity bits are found by negating the bits in this sum. Okay, so what is the sum? Well, we take the individual 16-bit patterns and we just add them with one's complements addition. And then we take the modulo 2 sum with FFF here. These are hex digits, so F is the bit pattern, it's 4 bits, 1, 1, 1, right? Okay, so by adding each of these 16 bits with FFF, we flip the bits. That's what we do. So this is a fancy way of saying we flip the bits in the sum here. And then one can show that the code word here has this nice property that D, our original data, plus the parity that we calculate in this way, it has internet checksum 0. So at the receiving end, if we want to check whether a pattern is a valid code word or not, we calculate its internet checksum. And if the internet checksum is 0, we know it's a code word, and then we accept it. If the internet checksum is not a 0, then we know it's not a code word, and then we reject it and declare an error. Okay. Small example to show, okay, one's complement. What is this? Well, I'm not going to go into a long story here, so I will keep it very brief. So one can see of this as regular n-bit binary addition, but with an end-around carry. So what is it really? Well, A plus B, if these are n-bit integers, then one's complement addition between A and B is equal to A and B if the result is less than 2 to the power of n. Okay. So whenever the sum is less than 2 to the power n, it's regular addition. However, when it's greater than 2 to the power of n, then it's A plus B, and then we subtract off this number, 2 to the power of n minus 1. Okay. So if one should look at this, an example, so if we have two 8-bit integers, 255, 225, and 155, that happens to be 16 bits are enough here. So if we want to hexadecimal, so this is the decimal number 225, it's E1 in hex, and it's 111100001 in binary. Okay, so these are the three different representations of the same number. Same thing we have here, 155 is 9B in hex, and 101, 1001, 1011 in binary. Okay, so if we want to calculate the one's complement sum of this, we take 225 plus 155, we get it to be 380, which is greater than 256. So then we subtract off 255. Okay, so 2 to the 8 minus 1 is 256 minus 1, 255 in this example, right? So 225 plus 155, 380, we subtract off 255, and this is the result. If we do this in binary addition here, we just do regular binary addition here. So 1, 1 is 1, 0. Okay, 1, 1 is 2, which is 1, 0, and so forth. And we just do the calculation. And then we see that we get 1 bit, which is not, okay, so the result is not a 16-bit integer, it's a 17-bit integer. And then we need to convert it into 16-bit integer. And that we do by taking this carry bit, the last bit, and we put that at the beginning and we add, and then we get this result. Okay. If we want to do that in hex, we get the same. We get a carry of 1, and we put that here, and then we get this. And of course, 125 in decimal is this in binary, and this is in hexadecimal. Okay, so it's the same thing. So whatever you do, you can pick and choose your favorite way to calculate this. Questions? Okay, so a small example of this to clarify things. So we have here our information word. It's a bunch of bits, right? And then we group them into 3 subgroups of 16 bits each. It happens that the number of information bits is a multiple of 16 in this case. Otherwise, we just have to add some zeros at the end to get it to be a multiple of 16 bits. Then we group them into 16-bit digits here in hexadecimal. So the red digits here is the red digits here, the blue one is the blue, and the green are the green. Okay? And then we just add them as regular integers. So if we do that in hexadecimal, the answer is this. You can check that by doing that in decimal, you get this. So these two numbers, the underlined with red here, are the same. So we see here that we get a carry bit here. So that needs to be added. So the carry bit here needs to be added to the result to get it to be a 16-bit integer. So we take the carry bit and plus 9C5F, and then the result is this. If we want to do that in decimal, we get the same answer, but we have to do different calculations. Okay, and then we flip the bits to find P. So this result, 9C60, 96C60, we take the modulo 2 sum with FFF, and you can trust me on that this is the result. Okay, it's just flipping the bits in that bit pattern. And then D plus P, D and then we append P would be then the information bits. These are the information bits. Oops, was ugly. Okay, so this part is the information bits, and here we have the parity bits. So P and D. And if we want to calculate the internet checksum of this, okay, we go through the same procedure. That is, we add the first 16-bit integer to the second, to the third, to the fourth. So we do that, and then we get 1 FFFE. We see that we have a carry, this one, which is the 17th bit, right? We need 16 bits. So we do wraparound addition to this, and then we get 001 plus FFFE, and then we get FFFFF, and then FFFF plus FFFF is 0. Okay, internet checksum 0. So error detection in the internet checksum is simply you take your bits that you get, you calculate the internet checksum of that. If that happens to be 0, you accept it. If it happens to be non-zero, you say an error has occurred. Questions? Yes?
Is it simple or hard to see where the error is, or do you just ask for the reason in the package?
Okay, so it's a very good question. So what do you do when you detect errors? As we will see later on in this case, we simply ask for a retransmission. So we don't try to figure out where the errors have occurred and correct them. Okay. third, so we talked about, okay, so is the internet checksum, is it any good? It's way better than the single parity check code, but it's still not super good, right? So it's something, it's far from being optimal, but it's decent, right? And it can handle more types of error events. One can say that this one is better than the single parity check code, but it's not perfect, right? The reason why this is used is because in the early days when the TCP and UDP and IP were defined, then all these calculations were done with general purpose hardware. So you used a regular CPU to do the internet checksums, and this is very efficiently implemented on a general purpose processor. Now, if you can afford specialized hardware, you can find you can do efficient encoding and decoding for better codes. But this was a compromise between a decent code and a low implementation complexity. Okay, so to find better codes, we want to go to, say, something called cyclic redundancy check codes, CRCs. And these are typically implemented with special purpose hardware. The hardware is simple, but you need to have it, right? So if you don't have the specialized hardware, it's a little bit painful to do this on a regular processor. Okay, but if you have specialized hardware, you definitely want to go to CRCs. So CRCs are used, for instance, in Ethernet, where on the Ethernet silicon, you have a hardware implementation of the CRC encoder and decoder. Okay, unfortunately, the theory behind CRCs is a little bit dense. It's very beautiful and nice, and yeah, it's actually pretty great theory. However, we don't have time to dive into this. I will just scratch the surface here a little bit and give you a feeling for what's going on. So to do that, we need to do a little bit of a detour into binary polynomials. Okay, so what is a binary polynomial? It's a polynomial where the coefficients are binary, so zeros and ones. Okay, so if we have a polynomial v of x here, x is some variable, right? And we don't specify what x is, it's just something. And then the coefficients in front of each power of x is a binary number. So all the v's here to the right are binary. And then we can think of a binary polynomial with degree n minus 1 as a representation of an n-bit vector, okay? So with degree n minus 1, what does that mean? It means that we have n coefficients, right? So so this one has degree n minus 1 because that's the highest power, but you see we need n coefficients to specify that, right? So it's a common rookie mistake to think that we can represent that to represent an n-bit vector we need an degree n polynomial. That's not true. We just need an n minus 1 degree polynomial. Okay, so we simply take the coefficients to the polynomial and we put them into a vector like this. Okay. So either we have this vector of coefficients or we have a polynomial. The two representations of the same binary string. Okay. So what can we do with this? Well, for instance, if we have a polynomial v and we multiply that with the power of x, say x to the power of m, so this is now a polynomial that corresponds to appending m bits to the right of v. And why is this the case? Because this polynomial now had degree which is greater than v, so it's more bits than v. But we see that we shift all the coefficients in the v polynomial to the left. So the highest degree coefficients is vn minus 1 down to v0, and then we insert m zeros to the right here. So if we have v to the x being x plus 1, for instance, and we say x squared vx, what is that? Well, it's x3 plus x2 plus 0 times x1, sorry, x1 plus 0 times 1, right? So we can think of this as being the binary sequence 1, 1, 0, 0, like this. Okay, so we stick the zeros to the right. This is corresponding to the 2-bit sequence 1, 1. Was that fairly clear? Okay. Addition of polynomials is done in a regular way. It's just that the coefficients are added, and since they're binary, we add them modulo 2. Okay. So armed with this theory of binary polynomials, we can do many things with these polynomials. We can add them together, we can divide them, and so forth. So binary polynomials can be divided just as regular polynomials. So if you remember that if we have a polynomial p, we can always write that as a product of two polynomials plus a remainder. Okay. So g here is called the divisor, and q is the quotient, and r is the remainder. So and the remainder here has a degree which is less than the divisor. Okay. So given a p and a g, we can calculate a q and a r to fulfill this equation. Okay, so that's a polynomial division for you. And the beauty with this is that we can find this quotient and the remainder by hand through long division, which is a slightly painful process. But for hardware, we can implement this very, very simple binary with logic, very simple logic circuit that's called with shift registers and binary address. Very, very simple to do. Okay, so it's painful to do by hand, but easy to do with hardware. Okay, so now CRCs. What are those? CRCs are codes, NK codes, so K input bits and output bits. And they're defined by a generator polynomial g, which has degree n minus k. So the degree of g is n minus k, which is equal to the number of parity bits or check bits. Okay. So we have k information bits as usual, and then we represent that by a polynomial now. Let's call it I for information. Maybe it should have been called D, but anyways, it's I now. So the n minus k check bits, we need to calculate them from I using G. G is what defines the code. I is the input to the encoder, and we want to calculate the check bits. And we find the check bits by dividing x to the power n minus k times I with G. Or in mathematics, we take the left-hand side here. So we have the information bits here. We simply multiply them with x to the power n minus k, which is saying that we take the information bits and we append zeros to the right. And then we divide it through by g. So g is given to us. So we calculate q and r. We don't care about q. We only care about r. And this r is then copied down to the code word that we transmit. So we have a systematic code here. So the code polynomial is the information bits plus the remainder. Okay, so which means that we have the information bits in the beginning here, ik minus 1 down to I0. So these are the k information bits. And then we have some check bits here to the right. Okay, so I realized that this was fairly quick, right? And it's hard to keep track of all the polynomials and the degrees and so forth. So I recommend that you check this, look at this slide, and try to figure out why it's correct. Okay, and then we'll do an example to figure this to explain the process of doing encoding here. Okay, so we have a code. Okay, so we have a code, CRC, which is specified by this generator. So we have different CRCs, different flavors, and all of them have different generator polynomials. But in this example, we have a very simple generator polynomial. It's x3 plus x plus 1, or if we write it out with the missing power of 2 here, it's x3 plus 0 times x2 times plus x plus 1. So in binary, it would be 1, 0, 1, 1. Okay? Now, we are given the task of finding the code word corresponding to these information bits. Okay? So it's a bunch of red bits here. And we would like to calculate then the check bits corresponding to this. So we know that the code word will consist of these red bits plus the check bits later on. How many check bits do we have? Well, we have a degree 3 polynomial here, so we have 3 check bits. Okay, so what we want to do then is we know G, we know I, we want to calculate R. Okay, so let's do that. Long division, it's not difficult, it's a little bit tedious, and sometimes it's hard to see on a piece of paper how this is done, so it's most easily done interactively like this. So what we have here is we want to calculate, in the left-hand side we have the red bits here, and we want to divide by G. Okay, so we would like to divide the left-hand side with G, and then we get Q plus the remainder divided by G. Okay, so the first thing to do is to write up the left-hand side like this, and then we start to do long division. So long division is that we start to the left, and then put in G here, and we line up the first one in the pattern here with the first one of this pattern here. And then we just add these together. Okay, so that's the first step in long division. So, and then let's get rid of that. Okay. So we see that the first one occurs here, and then we position G's first one just below it, and then we add them together, and then we see that 1 plus 1 is 0, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 0. Okay. And now we have a new bit pattern here, and we repeat the process. So we take G and position that so the first one in G is just below the first one in what's above it, like this. And then we add the result, and we get this. We position G, and we add. Position G, we add. And luckily here we got a lot of zeros here. So the next G will be positioned here. We add, keep on going, keep on going, keep on going, and keep on going. And finally, we have zeros here. And what we have to the right here is the remainder. Okay. The quotient is this. We don't care about the quotient, so you don't have to calculate that. But we do care about the remainder, because we know. Okay, so the quotient is the blue bits here, but we only care about the remainder. And why is that? Well, it's because the code word consists of the information bits, the red bits, plus the remainder at the end. Okay. So, and this calculation, which is done here, is very easily done by shift registers and so forth. Just one final word before we finish today. So common CRC codes is the CRC32, which has this polynomial. And it's used in these protocols, including Ethernet, that we will talk a little bit more about later on. So these are the frame check bits are calculated in Ethernet by a CRC32 with this polynomial. So this polynomial is standardized, right? There are many polynomials of the right degree, but this is the polynomial that we're looking for when we do a CRC32. So it has 32 check bits. Okay. The CRC16 has this polynomial, and that's used in all of these protocols. Bluetooth, maybe you recognize. There's some other that you might or might not recognize here. There is a CRC1, which is a very simple one, and it's actually the same as the single parity check code that we talked about in the beginning. Okay, so that used in many hardware. Okay. Okay. Now, before we finish, we are lagging a little bit in the lecture schedule, so I need to figure out what to prioritize a little bit. So I'll do some thinking about what we need to do, but we're lagging a little bit, so the reading schedule is a little bit offset from what we're going to talk about at the lectures. For your projects, you will need error detection as part of part 2. Part 2 also consists of, actually is about implementing a retransmission protocol called stop and wait. We'll talk about that on Thursday. But if you want to start a little bit on looking at part 2 of the project, you can do that already. Question?
Next Thursday or Tuesday?
Today is Thursday, right? So Monday. Sorry. Mixed up with days here. But we'll talk about stop and wait on Monday. Yeah, have a nice weekend.